Place two perfect clocks in the same room. Put one on the floor and the other on a desk. They are identical. They begin at the same instant. Nothing touches them, and neither is defective. Yet the clock on the desk will run slightly faster. Raise a clock by only 1 centimeter near Earth's surface, and its rate changes by roughly 1 part in 10 to the 18th. Over a year, that difference amounts to only a few tens of picoseconds, a few tens of trillionths of a second. An ordinary clock cannot see it. The best clocks humans have built can. This is not a flaw in the clock. It is a property of time. Einstein's general theory of relativity says that mass changes the geometry of spacetime. Clocks at different gravitational potentials do not accumulate time at exactly the same rate. A clock closer to Earth runs more slowly than an otherwise identical clock placed higher above it. That once sounded like a philosophical consequence of an abstract theory. Today, it is an engineering measurement. Optical atomic clocks have become sensitive enough to resolve relativistic differences across laboratory scale heights. Researchers have even measured the gradient across a sample of atoms only about a millimeter tall. At this precision, a clock no longer tells us only when something happened. It also becomes a sensor for where it is in Earth's gravitational field. Compare two sufficiently accurate clocks, and the difference between their ticking rates reveals a difference in gravitational potential. Potential is related to height, but it also depends on the distribution of mass. Mountains, groundwater, ice, magma, and dense rock all contribute. In principle, time can help us map Earth. The field is called chronometric geodesy. Geodesy is the science of measuring Earth's shape, gravity field, and orientation. Chronometric means that time itself becomes the measuring instrument. This is not as simple as placing a wristwatch on a mountain. It requires atoms controlled in vacuum, ultrastable lasers, and communication links capable of comparing distant clocks without erasing their precision. Most such systems remain complex laboratory instruments, although portable versions are beginning to appear. At the same time, the international measurement community is preparing for a historic change. Since 1967, the second has been defined using a microwave transition in cesium atoms. Optical clocks now outperform the best cesium standards so decisively that metrologists are working toward a future optical definition of the second, potentially in 2030 or later, if strict international criteria are met. So this is more than a story about a better clock. It is the story of a timekeeper becoming a gravity sensor, a relativity experiment becoming a surveying instrument, and a laboratory technology becoming a possible way to monitor a changing planet. To understand how that happened, we first need to ask a deceptively simple question. What exactly is 1 second? For most of human history, timekeeping began with astronomy. A day followed Earth's rotation. A year followed Earth's orbit around the sun. Early clocks divided those cycles into smaller intervals, find something that repeats, count the repetitions, and call the count time. The problem is that Earth is not a perfect clock. Its rotation varies slightly because of the atmospheres, oceans, movement inside the planet, and the moon's gravitational influence. Navigation, telecommunications, and science require a reference more reproducible than a slightly irregular planet. Atoms offered one. Every atom of a particular isotope has the same internal structure. Its electrons can occupy specific energy states. When electromagnetic radiation has exactly the right frequency, the atom can move from one state to another. That resonance is a natural reference that can, in principle, be reproduced anywhere. Since 1967, the second has been tied to cesium-133. The official definition fixes a particular cesium transition at exactly 9,192,631,770 Hz. Those microwave oscillations act like marks on an extremely fine ruler. Cesium fountain clocks cool atoms until their random motion becomes very small, launch them upward, and let them interact with microwaves as they rise and fall. Repeated measurements show whether the applied frequency is above or below the natural resonance. National laboratories use such standards to realize official time, while hundreds of clocks contribute to international atomic time. But microwave clocks still provide a finite number of divisions per second. A ruler marked in millimeters resolves smaller differences than one marked only in centimeters. In the same way, a higher frequency transition offers a finer ruler for time. Optical clocks use transitions associated with visible or near visible light, whose frequencies are tens or hundreds of thousands of times higher than the cesium microwave frequency. More ticks create greater potential resolution, but frequency alone is not enough. Atoms move. They collide. Heat, electric fields, and magnetic fields can shift their energy levels. The laser can wander. Even the device used to trap the atoms can disturb the transition being measured. This is why an optical clock looks less like a clock and more like a precision physics laboratory. Lasers cool the atoms. Vacuum systems remove almost all background gas. Optical cavities stabilize the clock laser. Researchers suppress motion and environmental fields, then calculate how much every remaining effect could bias the result. Two concepts are important. Accuracy describes how closely the corrected clock frequency represents the unperturbed atomic transition. Stability describes how consistently the clock repeats its measurement and how quickly random noise averages away. A clock can be stable but biased. It can also be accurate in principle but so noisy that proving its accuracy takes weeks. The best systems must master both. Researchers found several promising atoms and ions, including strontium, ytterbium, aluminum, and mercury. But optical light oscillates far too quickly for ordinary electronics to count directly. The invention that solved that problem was the optical frequency comb. An optical frequency comb turns the oscillations of light into something countable. Its spectrum contains a series of evenly spaced frequencies, like the teeth of a comb. Their spacing can be connected to microwave signals that electronics can measure. The comb therefore bridges the optical and electronic worlds. It is a gearbox and a ruler for frequency. With it, scientists can measure an optical transition, compare clocks operating at different colors of light, and connect optical standards to the microwave systems that still distribute civil time. The atoms themselves are usually controlled in one of two architectures. A trapped ion clock suspends a single charged atom inside a vacuum chamber using electromagnetic fields. Lasers cool the ion and probe a very narrow transition. If the laser has the right frequency, the ion changes state. Repeating the test tells the system how to steer the laser. One ion experiences almost no atom-to-atom collisions, which supports excellent accuracy. The trade-off is signal strength. One atom provides one response at a time. An optical lattice clock uses hundreds or thousands of neutral atoms. Interfering laser beams create a standing wave pattern, forming microscopic trapping sites. The atoms are held nearly motionless, and their combined response produces a stronger signal and exceptional stability. But the trapping light can shift atomic energy levels. Researchers solve this with a carefully selected magic wavelength. At that wavelength, the trap changes the two clock states by nearly equal amounts, so the frequency difference between them remains almost unchanged. Every part of the instrument is a negotiation. Cool the atoms without disturbing the measurement. Trap them without shifting the clock transition. Isolate the laser while still delivering it across an optical table. Remove gas molecules while accounting for thermal radiation from the chamber. Extend the interrogation time without allowing the laser to lose coherence. The result is delicate, but it can measure frequency at 19 decimal places. In 2025, the United States National Institute of Standards and Technology reported an aluminum ion quantum logic clock with a systematic fractional uncertainty of 5.5 times 10 to the minus 19. Aluminum is an excellent clock atom, but it is difficult to cool and read directly. The NIST design pairs it with a magnesium ion. Magnesium cools the pair and allows the aluminum state to be detected through quantum logic spectroscopy. The improvement did not come from one magical component. Researchers redesigned the ion trap, reduced background hydrogen in the vacuum system, and transferred an ultra-stable laser over several kilometers of fiber. A frequency comb connected that laser to the clock. Each weak link was measured and improved. Popular explanations say that a clock of this class would lose less than a second over the age of the universe. That analogy communicates scale, but metrologists prefer quantities that can be tested, fractional uncertainty and stability. These clocks have not actually run for billions of years. Still, the intuition is useful. At roughly 1 part in 10 to the 18th, familiar language begins to fail. And at that precision, relativity is no longer a correction added after the experiment. The clock cannot be fully described without knowing its height, motion, and gravitational potential. Its position on Earth becomes part of its uncertainty budget. That is the moment a timekeeper becomes something else. General relativity says there is no single universal rate at which time passes everywhere. Near Earth, a clock deeper in the gravitational field accumulates slightly less time than a clock at a higher potential. When the two are compared, the lower clock runs more slowly. For a small vertical separation near the surface, the fractional frequency difference is approximately gravity multiplied by height, divided by the speed of light squared. The result is about 1.1 times 10 to the minus 18 for every centimeter. Nothing feels abnormal beside either clock. A scientist next to the lower one does not experience delayed thoughts or slowed speech. Every local process follows the same local time. The difference appears only when the clocks are compared. An optical clock is not detecting a force pushing on imaginary hands. It realizes a local atomic frequency. Relativity determines how that frequency compares with an identical clock elsewhere. The effect was first tested over large height differences with clocks on aircraft, rockets, and satellites. The global positioning system must account for both gravitational and motion-related relativity, otherwise its timing would quickly become unsuitable for accurate navigation. As clocks improved, the experiment shrank. In 2010, NIST researchers measured the relativistic difference between optical clocks separated vertically by roughly 1/3 of a meter. In 2022, researchers working with ultra-cold strontium resolved a gravitational frequency gradient within a single atomic sample only about a millimeter tall. Different portions of the same ensemble occupied slightly different gravitational potentials. Time's gradient had become visible inside the apparatus. But height is only an approximation. Earth is not uniform. Mountains, ocean trenches, groundwater, sediment, ice, and deep geological structures distribute mass unevenly. The planet also rotates, adding a centrifugal contribution. A clock fundamentally responds to the combined gravitational and rotational potential at its location. Surfaces with equal potential are called equipotential surfaces. Water at rest follows them. The geoid, often described as mean sea level extended beneath the continents, is a reference surface tied to that potential. This creates a crucial distinction between geometric height and physical height. Satellite navigation can determine position relative to a smooth mathematical ellipsoid. Engineers concerned with drainage, construction, flooding, and sea level often need height relative to the gravity field. Water does not care about a coordinate system. It responds to potential. Traditional geodesy combines precise leveling, gravimeters, satellite observations, and mathematical models. Each method has limitations. Leveling errors can accumulate over long distances. Satellite positioning does not directly measure gravitational potential. Gravity surveys require dense observations and interpretation. Optical clock comparisons provide a different observable. Instead of inferring potential only from geometry and gravity measurements, the clocks respond directly to a potential difference through the rate of time itself. This is chronometric geodesy. It turns Einstein's theory into a surveying tool. Imagine two national laboratories connected by phase-stabilized optical fiber. Each operates an optical clock. A laser carrying one clock's rhythm travels through the link. An active system detects and cancels noise introduced by vibration and temperature changes in the fiber. After accounting for the clocks and the link, the measured frequency ratio reveals a difference in gravitational potential. That result can be expressed as an equivalent height difference. More importantly, repeated measurements could reveal change. Groundwater moves mass. Ice sheets gain and lose it. Magma migrates. Tectonic processes deform the crust. Oceans and the atmosphere redistribute weight. These processes can change both a clock's elevation and the potential surrounding it. A future clock network could contribute to monitoring some of those changes. The word contribute matters. Clocks would not replace satellites, gravimeters, seismometers, or geological models. A frequency shift may have several causes. The clock moved, nearby mass changed, an environmental field disturbed the atoms, or the transfer link added residual noise. Interpreting it requires other sensors and careful modeling. The realistic vision is sensor fusion, with clocks adding a new observable. Potential is especially valuable because it determines where water flows. Clock comparisons could help connect national height systems that rely on different historical reference points. They may improve height consistency across long distances and eventually support research on groundwater, volcanic systems, crustal deformation, and sea level reference surfaces. NIST has discussed a possible future network with clocks separated by tens of kilometers. This is a proposed architecture, not a deployed planetary system. The best instruments are still costly, fragile, and usually operated by specialists. Yet networking has already begun. In 2025, a coordinated European experiment compared 10 optical clocks across 6 countries, measuring 38 frequency ratios over thousands of kilometers. In parts of the network, optical fiber links achieved around 100 times greater precision than satellite comparison. The campaign also found inconsistencies, showing how much work remains before optical clocks can routinely support international timekeeping. That mixed result is authentic engineering progress. The clocks are precise enough to expose weaknesses in the infrastructure used to compare them. The work is global. NIST and American university laboratories are advancing ion clocks, lattice clocks, and relativistic geodesy. The United Kingdom's National Physical Laboratory develops strontium and ytterbium systems, portable clocks, and international frequency comparisons. Australia has invested in portable optical clocks for positioning, navigation, and timing tests, including environments where satellite navigation is degraded. Their motivations differ, but the core technology is the same. Use an atomic transition as an extraordinarily stable reference, then compare it without losing the information. Optical clocks also reach beyond geodesy. Different atomic species may respond differently if a fundamental constant changes. Long-term frequency ratio measurements can therefore test whether constants such as the fine structure constant remain stable. Clock networks have also been proposed as detectors for certain dark matter models that could briefly alter atomic transition frequencies. These are searches, not discoveries. Precision clocks are valuable because they turn small theoretical possibilities into measurable constraints. The practical turning point will be portability. A laboratory clock cannot easily visit a remote coast, mountain, or tunnel. Transportable systems are becoming smaller, but they still require lasers, vacuum equipment, environmental control, and expertise. The breakthrough will not be a clock that is merely compact. It will be one that is accurate, stable, transportable, continuously operable, and trusted by people who did not build it. That is the difference between a scientific demonstration and infrastructure. Optical clocks have created an unusual problem. The official definition of the second is no longer based on the best performing kind of clock. Cesium remains the foundation because an international unit cannot change whenever one laboratory sets a record. A definition must be reproducible across countries, connected to existing timescales, and stable for decades. It must preserve continuity so that a second after the change is, for practical purposes, the same duration as a second before it. The international community has therefore created a roadmap rather than a race. The present target is an important decision around 2030. With adoption in 2030 or later depending on mandatory criteria. Those criteria cover clock performance, agreement between independent systems, reliable contributions to international atomic time, access for national laboratories, and methods for disseminating the improved unit. One question is what the new definition should use. It could select a single optical transition, producing a structure similar to the current cesium definition. Strontium and ytterbium are among the leading candidates. A second option would use a weighted combination of several optical transitions. An ensemble would include multiple mature technologies, but make the definition more complex. There is also a geographic barrier. Fiber links can compare clocks at extraordinary precision across continental distances. Global timekeeping also requires links across oceans and regions without advanced fiber infrastructure. Current satellite methods cannot transfer the full performance of the best optical clocks. Free space optical links, transportable clocks, and future space systems may help, but they must become reliable and accessible. Then there is the gravitational problem created by the clock's own success. At the 10 to the minus 18 level, a height error of 1 centimeter matters. Laboratories must know their gravitational potentials to compare clocks properly, yet clocks themselves can measure potential differences. Time metrology and geodesy become interdependent. At lower precision, a laboratory floor looks fixed. At optical clock precision, it moves with tides, atmospheric loading, and geological deformation. Thermal radiation from the chamber affects the atoms. Electric and magnetic fields shift energy levels. The definition may be simple on paper, but realizing it requires measuring the environment. A future redefinition will not make a phone, oven, or wristwatch visibly run differently. Existing time services will preserve continuity. The immediate benefits will appear in the highest precision work, fundamental physics, navigation research, synchronized networks, radio astronomy, space missions, geodesy, and national measurement systems. The larger consequence is conceptual. For centuries, maps told clocks where they were. A laboratory used its location to correct for gravity. Now the relationship is becoming reversible. Clocks can tell maps something about the world. A pair of optical clocks can compare gravitational potentials. A network can watch those potentials change. Different atoms can test whether nature's constants remain constant. An instrument built to divide a second becomes sensitive to centimeters, moving mass and the geometry of spacetime. This does not mean clocks will replace every surveying tool or reveal every structure beneath Earth. Their signals are subtle, their systems remain difficult, and many applications are still research goals. But the foundation is established. A higher clock ticks faster. Optical clocks can resolve that difference at human and even subhuman scales. Laboratories are comparing them across borders. The international measurement community is preparing to let optical transitions define time itself. We built clocks because we wanted a stable answer to the question, when? Precision has forced us to ask another question, where? The most accurate map of the future may begin not with a ruler, a camera, or a satellite, but with two clocks asking how fast the universe allows each of them to tick. Time is not level. And for the first time, our clocks are precise enough to map the slope.